cis-diaqua, dicyano. We can leave out the cis if we want to there. It's cobalt 3. In the third case, we now are going to move the two aqua groups to the trans positions and let the amine groups go to the cis positions. So in this case, we have cis-diamine, trans-diaqua, and that forces the two cyano groups to be cis as well. So we can leave the cis out, it's implied. So the name for this compound is cis-diamine, trans-diaqua, dicyano-cobalt 3. In the fourth case that we looked at, we forced the dicyano cyano groups to be trans to one another. So here we name it cis-diamine, cis-diaqua. We have to include the trans here. Trans-dicyano-cobalt 3. Why? Because you can have a configuration where the amine group, the amine groups, the aqua groups, and the cyano groups are all cis to one another. Such as this. And this is where you get into the idea of geometric and optical isomerism. So in this case, you have all of the three different types of ligands cis to their counterpart. So you can see here clearly that the two water groups are cis to one another, the two cyano groups are cis to one another, and the two amines are also cis to one another. So we name this cis-diamine, cis-diaqua, cis-dicyano-cobalt 3. And we have to use the RS nomenclature to go along with that, the rectus and sinister, as you learned in organic chemistry. It is reviewed in your textbook. I don't ask you to identify whether it's rectus or sinister according to, because it's hard to tell. And that's beyond the scope of this class, but you need to be able to recognize if you have all three types of ligands cis to one another in an octahedral complex, that means it has an R or S configuration. Just a little bit more on geometric isomers. What this table shows is the following. It takes and looks at the number of unique ligands bound to a metal cation in an octahedral geometry and gives you the general formula. So D, E, and F are all just monodentate ligands that can bond to the central metal cation. And in this last column we talk about the total number of geometric isomers and include, in parentheses, the number of pairs of isomers that are enantiomers. So if, in the first case, which we've already looked at, we have three unique ligands, and the formula is Ma2B2C2, that means we have a total of 6 possible geometric isomers. And like we've shown, there was one pair. That means 2 of those isomers are enantiomers. That's the RS configurations that we looked at just shortly ago. If we have 4 unique ligands bound to the metal cation, A2, B2, CD, that gives us 8 possibilities with 2 pairs of enantiomers, or 4 total isomers that are optically active. Fifth, or if we have 5 unique ligands, that gives us a formula of Ma2BCDE. The total number of geometric isomers is 15, and that means 6 pairs, 12 out of the 15 isomers are enantiomers. Finally, if we have 6 unique ligands, that would mean that the formula would be MABCDEF, giving you 30 total geometric isomers, and all 30 are optically active. There are 15 pairs of enantiomers. At the bottom here, I'm showing a way that you can use to determine or draw all the isomers systematically. And what I'm going to do is write out an example and post it on Moodle so that you can take a look at it in your own time and work through understanding how you find all the isomers for a given formula.